Hello and welcome to class 11 students. If you started studying physics in class 11, I'm sure people have started to advise you to first start studying a bit of basic maths. Things like vector algebra, differentiation, integration. And quite honestly, it feels a little scary at first, right? Especially if you've had no exposure of calculus in younger classes. Also, I've seen teachers in books bombarding the students with calculus formulas, differentiation formulas that you're just asked to memorize before you start studying physics. And if you've been a student who likes to understand science and do everything with reasoning, it would feel such an ugly start to class 11. Just mug up differentiation formulas first before you start to study any chapter of physics. So today I want to make the process more natural for you. I want to introduce the concept of differentiation by involving the first chapter of physics that you have, which is motion in a straight line. And if you watch carefully to the end, I'm very sure that you'll not only understand what is differentiation, even the formulas that you're otherwise asked to memorize will start making sense to you. And I would like to begin my discussion with a question, simple question. Look at this. There's a body that moves on a straight line, and to track the position of the body, I've marked different numbers on the line on which this body is going to move. So basically this body is moving on a number line. Of course, because the body is moving, we can say that the body is changing its position with time. And so to describe its motion more precisely, I also want to inform you how exactly does it change its position with time. If x is the position of the body on this number line, here I tell you that the position of the body changes with time as x is equal to 3t. So basically, you can put in different values of time in this equation and you're going to get different values for the position of the body. So basically, if you put t equals to 4, you will know that the body is going to be at x is equals to 12 on the 4th second. X is equals to 12 is going to be somewhere on the number line, right? So looking at this equation, you realize that at different moments in time, the body is going to be at different positions on the number line. Having understood that, there are two questions that I want you to answer. The first one is, where is the body at t equal to 5 seconds? Well, that's pretty easy. You just put 5 in place of t, you get the value of x as 15, and so you realize that at the 5th second, the body is at x is equal to 15. Might be somewhere here. Great, easy question. Now let's read the second question. What is its speed at t equal to 5 seconds? So now I don't care about where the body is at t equal to 5, but rather I want to know how fast the body was moving at t equal to 5 seconds. That is, at the 5th second, how fast the body was. Now if you notice very carefully, I have attached a speedometer onto the body. Let me zoom in. Here, have a look. I have attached the speedometer to the body, and so basically my question is that at the 5th second, what speed will the speedometer be showing, right? That is the meaning of my question. That at the very 5th second, what is the speed of the body? Now, luckily for us, in this particular situation, we are dealing with a very convenient case, When you start to observe how the position of the body changes with time for this particular equation, you find that the position of the body is directly proportional to the value of time. Meaning every 1 second, the body covers an additional 3 meters. See, 0 to 1, body's position changes from 0 to 3, then 3 to 6, then 6 to 9, 9 to 12 and so on. So we can say per unit time, that is per second, the body always covers a distance of 3 meters. And in fact, that is how we define speed, right? Speed is the distance covered per unit time. And here, no matter where you pick your 1 second interval, you may observe the body from the 2nd to the 3rd second, or the 5th to the 6th second, or the 100 to 101st second. In any of these 1 second interval, the body will always cover a distance of 3 meters, which means that the speed of the body is simply 3 meters per second. And it's always at that speed. So the case we are dealing with is actually of a body that is moving with a constant speed. So if we were to answer what is the speed of the body at the 5th second, well, just because the speed of the body is always the same, and we figured out that per second the body covers a distance of 3 meters, we realize that the speed of the body is always 3 meters per second, and therefore at the 5th second the speed of the body must be 3 meters per second. And so that's the answer to the second question. 3 meters per second. Here I want you to understand that even though we define speed as distance covered per unit time, for a body to really be moving at a constant speed, it not only must cover the same distance every 1 second, but rather it must be covering the same distance for any fixed interval of time that we pick, however small or large this interval may be. Of course, we saw that every 1 second this body is covering 3 meters, but even if we took a shorter interval of time, let's say every half second, then also we would find that every half second, the body always covers 1.5 meters. You can keep putting t as first 0, then 0.5, then 1, then 1.5, then 2 and calculate the corresponding values of x. You'll always still find that for every half second, the body covers the same fixed distance of 1.5 meters. In fact, I also want you to understand this graphically. Here, if I make a plot of the position of the body with respect to time, you understand plotting, right? When t is 0, body is at 0. When t is 1, body is at 3. If on the x-axis I mark time and on the y-axis I mark position, then I can plot points like 0, 0, 1, 3, 2, 6 and so on to get a graph that represents the relationship between the position and the time. And here, since the position is directly proportional to time, when you do make a plot, you're going to get a straight line. See, here I've made a rough plot. Of course, as time increases, the value of x increases and it always happens at a fixed proportion. That is why this plot is a rising straight line. Now also notice when I pick a fixed interval of time, whatever duration this might be, I can pick a larger interval of time or an even smaller interval of time. I want you to look at the change in the values of the position of the body. You see, at this moment, the body's position is here, right? At this value. And when some time passes and the body moves, its new position is given by this value. Let me mark the old and the new position. So now see, as the time changes from this value to this value, the position changes from this value to this value. Now what is noteworthy here is that no matter where I pick this interval of time, whenever I pick it, I will always find the same change in position. So let me pick this same fixed time interval somewhere else at some other time. So I'm going to copy the exact same interval. You can see it's exactly the same, but place it elsewhere. Let's say here. So now when the time changes from this value to this value, we'll measure how much has been the change in the position, right? So let me draw the horizontal lines. So earlier the change in position was this much and now the change in position is this much. Now is this change in position and this change in position exactly the same? Let's lift these two lines up and match it with these two lines and let's check if the gap is the same. Do you see the gap is exactly the same? Which means when we took a fixed interval of time, no matter when we take it, we always see that the body always moves the same distance in that fixed interval of time. And this would be true for any interval I take. I can repeat the exact same comparison by taking a shorter interval of time, both the times. Of course, then I'm going to get a smaller change in position, but still when I compare the change in position to another change in position for the same time interval, the two changes in position would still be equal, which really goes to show that the body is truly moving at a constant speed. So in conclusion, I can say, let me erase the extra stuff and then tell you my conclusion. So in conclusion, I want to say that for this moving body, whenever I pick a certain interval of time and I measure how much distance it has covered in that time, I will always find this distance covered by time taken to be a constant value. That constant value in this particular question was 3 meters per second. I mean, we can easily take some numbers in place of our time and find that. Let me show that too. So let's say at t is equals to 2, I know since x is equals to 3t, the body would be at x is equals to 6. And if I take, let's say t is equals to 5, then at the 5th second, the position is going to be 15. So in these 3 seconds, how much did the body move? 15 minus 6, 9 meters. So therefore, what is the distance covered by the time taken wala value? It's 3 meters per second. And no matter what values of time I took, I'll always end up getting the same value for change in x by change in time. And it's 3 meters per second for this example. Is this question clear? So we see that both these questions were very easy to answer because we were dealing with a convenient special case where the body was moving at a constant speed. But what if that is not the case? Now look at another similar yet different question. That's a very similar situation. The body is moving on the number line and all of that is still there. But now the position is changing with time following this equation. Of course, still as time changes, the position changes. But now the position and time are not directly proportional. Now x is equals to the square of t. Now sadly in this case, the body is not moving at a constant speed. And it doesn't take too much to really declare that. Simply check that if I take the first 1 second, the body covers 1 meter. But when I take the next 1 second, then the body covers 3 meters. So now when I keep picking 1 second intervals, the distance covered by the body in these different 1 second intervals are all different. So this is definitely a body that is not moving with a constant speed. In fact, if you keep tracking the distances covered by the body every 1 second, you'll see that the value of the distance covered keeps increasing. First it covers 1 meter, in the next 1 second it covers 3 meters, in the 1 second after that it covers 5 meters and so on. So the value of distance covered per unit time is not a constant anymore. In fact, it keeps increasing. So even though we can easily still answer the first question, where is the body at t equal to 3? Well, the body will be at x is equals to 9, somewhere here. But it's the second question that will start troubling us. What is the speed at t equal to 3 seconds? So we know, okay, at the third second the body is somewhere here at x equal to 9. But when the body is exactly here, what speed does the speedometer show at that very moment? Now that becomes a very interesting question to ask. Now think about it. How would we know the speed at the third second? Now this time if I make a plot of the position versus time for this body, because the position is no longer directly proportional to time, we won't have a straight line plot anymore. Let me show it to you. See, as time passes by, the position starts changing more rapidly. Now again here, if I decide to take a certain interval of time, let me drag it here. Now this might be any interval of time. Notice as the time changes from this value to this value, the position changes from this value to this value. Can you see roughly it is this much change in position? This much, right? Now when I take the very same interval, but later on, so let me paste it here. Notice how at a later interval, it's the same exact interval though. If this were 2 seconds, this is also 2 seconds. But this time the body is showing a huge change in position. So in the same fixed interval of time, the body first showed a small change in position, but later on showed a significantly greater change in position. So this time if I'm measuring the value of change in position by change in time, this ratio no longer remains a constant. It'll come a small value here, but a much larger value here. Because for the very same interval of time, now we have larger value of delta x. So since the numerator increased, the ratio also became higher. So change in position by change in time is no longer a fixed value. All this explanation just to show to you that this body is not traveling at a constant speed. I'm sure you had understood it anyways. So now coming back to the question, how would we find what is the speed at the third second? Now remember in the last question, because the speed of the body was always 3 meters per second, we very easily had answered that the speed at the 5th second was also 3 meters per second. But now for this body, the speed is changing every single moment. The value that the speedometer shows when the body is here versus when the body is here versus when the body is here, they're all going to be different. Now at t equal to 3, the body is at x is equal to 9. So now we must concern ourselves with what is the speedometer going to show when the body is exactly here at x is equal to 9. So let's forget what happened before that or what is going to happen in the distant future. Let's just focus at the time when the body is crossing the point x is equal to 9. Let's say you observe the body from t equal to 3 to t equal to 4. So basically you are observing it for 1 second. From t equal to 3 to t equal to 4. How much distance does the body cover in this duration? Well, it will go from x is equal to 9 to x is equal to 16. So in this 1 second of observation, we'll find that the body covers a distance of 7 meters. So now could we say that at t equal to 3, the body was moving at 7 meters per second? Sadly, we cannot. Do you realize that if we observe for 1 second, from t equal to 3 to t equal to 4, and even during this 1 second, the body must have increased its speed a little bit. It did not travel with a constant speed from x is equals to 9 to x is equals to 16, which means that the speed we calculated, 7 meters per second, the speedometer won't be showing that fixed value of 7 meters per second for this entire 1 second duration. So what kind of speed have we really calculated? This 7 meters per second. Well, if we divide the total distance covered in this 1 second divided by the duration, we are merely finding an average speed of this 1 second interval. This speed is not really the speed at the third second, but rather an average value from t equal to 3 to t equal to 4. In fact, let me write the calculations here. So when we observe the body moving from t equal to 3 to t equal to 4, the position changes from 9 to 16. So the distance covered in this 1 second would be 7 meters. So this change in x by change in time comes out to be 7 meters per second. Let me write it. But remember, this is only an average speed. So if we truly want to find what is the speed at the third second, we can't be observing the body for such a long 1 second duration. We want to observe the body for a very short duration. So to know what is the speed of the body at exactly the third second, we would rather want to observe the body for a shorter duration so that we get a more accurate value for the speed of the body close to the third second. Let's say we observe it from t equal to 3 to t equal to 3.5. That is for half a second. Let me change the values. So now the body is going to go from x is equals to 9 to what value? Well, remember x is equals to the square of t. So the square of 3.5, which is 12.25. Let me write it. So this time in the half second that we observe, the body has moved a distance of 3.25 meters. So now what is the distance covered divided by the time taken? It's 3.25 divided by 0.5. which is 6.5 meters per second. I'll write it here. But still, can we say that this is really the speed of the body at the third second? Well, at least we have done better since last time. We observed the body for just half a second on t equal to 3, and then when we did distance covered by time taken, we got 6.5. But don't you think this is also an average speed over this half second and not truly the speed at the third second? We can say that at the third second the speed is roughly 6.5, but remember, for this body the speed is always increasing. So even from t equal to 3 to t equal to 3.5, the speed of the body must have increased, and this value is just an average over this interval. So to find the answer for what is the speed at the third second, for how long should I observe the body? So to find what is the speed at the third second, I must observe the body for an even shorter interval of time. What if I took just 0.1 seconds? So when we observe from t equal to 3 to 3.1, the body would move from x is equals to 9 to x is equals to 9.61. The square of 3.1 is 9.61. And so then we can say that when we observe the body for just 0.1 seconds, when our clock strikes the third second, we look at the body for just 0.1 seconds, and we see that in this tiny interval of time, the body covers a small distance of 0.61 meters. Because it has moved from 9 to 9.61, it covers 0.61 meters. So if it covers 0.61 meters in 0.1 second, what must the speed of the body be? 6.1 meters per second. Let me write that. But still, can we say that this is the actual value of the speed at the third second? By now you must have realized that I have pushed you into an endless pursuit of trying to find an accurate answer for what is the speed at t equal to 3. I mean, we took a 0.1 second interval, right? So one can argue this is still an average over this 0.1 seconds. Even during this 0.1 second, the speed of the body is going to increase a little bit. So this is still an average value. In fact, even if I took 0.01 seconds, like I've done over here, I would find that the change in position is 0.0601, and then the speed value would come out as 6.01 meters per second. Let me write that. But then again, this is only an average over this 0.1 second. Of course, now this answer is a much better answer than the first answer we got, 7 meters per second, when we had observed from t equal to 3 to t equal to 4. But this is still not the best we can do, right? But now you'll complain that, sir, whatever interval we take here, there will always be a shorter interval which would give an even more accurate answer. But if you observe the trend of what has been happening, first the answer was 7, then it became 6.5, then 6.1, then 6. You'd realize that we are heading towards a certain value. What is that value? It is 6. And we start to get this very strong feeling that the answer for the speed at the third second might be 6 meters per second. But how do we prove this feeling? See, the problem is that all this time, in all of our observations, we've been observing the body for a long duration. First we had observed for 1 second, then half a second, then 0.1 seconds. And the argument is that the speed calculated from such observations are only merely average speeds over those intervals. Now, how small would you want this time interval to be for the answer to truly be accepted as an actual speed at the third second? How tiny short should your observation be? There's no limit, right? You might do your calculations for t equal to 3 to t equal to 3.000000001 second. But some other crazy guy who's more obsessed with accuracy could do it for t equal to 3 to 3.00000000001 second, and will argue that now I have a better answer. My question to you is, what should this value be for our answer to be the best answer? Should it just be 0? Not really. Because if we observe the body for 0 seconds, it would mean that we are not even letting the body move. It's like we are looking at an image of the body at the third second. But understand, only if we let the body move can we comment on the speed of the body. We need to watch a video of this body to comment on its speed, not just an image. So if we observe for 0 seconds, how can we know how fast the body is moving? It's like saying that at t equal to 3 the body is at 9, and then again at t equal to 3 the body is at 9. If you don't let time pass, you can't know how fast the body was moving. 0 is not what we really want here, but we want something very close to 0. We want something that is as close to 0 as possible and is yet larger than 0. You're getting my feeling, right? Now, good for us, in mathematics we do have a number that represents this very tiny feeling. Anyone knows what that number is? It's not a real number actually. The number is called 0 plus. 0 plus is a number as close to 0 as possible yet larger than it. Is 0 plus equal to 0.0000000000001? No, it is not. It is even smaller. You can never really use a finite set of digits and express the value of 0 plus. It's more of a feeling than an actual number. Very much like infinity. in some sense it is opposite to the size of infinity. This time it's an infinitely small number. So only if we observe this body for 0 plus seconds can we say that the speed we found by measuring the distance covered in that 0 plus second would be the true speed at the third second. I mean, we can't do any better, right? But the problem now becomes the calculations. We knew how to find the values of x for real values of t, like 3 and 3.01 and so on. But how do we deal with the mathematics of this unreal number, 0 plus? So let's do something. Never mind 0 plus. So far, we've always been observing body for some time. First, we did it for 1 second, then 0.1 second, then 0.01 second. Let's say we observed the body for h seconds. Some variable, and then I'll just calculate what is the distance covered divided by the time taken, and whatever the value comes, we'll say that is the average speed over those h seconds. Nobody is going to argue that, so let's do it. So remember, we are going to observe for h seconds, which means we are observing from t equal to 3 to t equal to 3 plus h. So tell me, where would the body go from x is equal to 9 to what value? Well, x is equals to the square of t, and later when t becomes 3 plus h, the value of x will be 3 plus h square, 3 plus h whole squared. So now what is the distance covered? Well, the position changes from 9 to 3 plus h whole squared. So the distance covered would simply be the difference between the two. And I've written it here that the difference in the position is the distance covered divided by the time taken, which is h seconds. Let's do the calculations now. The plus 9 cancels out with the negative 9. Now notice how we can factor out h from the numerator. And now our calculations are telling us that the average speed for this h second interval has come out to be 6 plus h meters per second. But this is an average speed over the h seconds interval. If we truly want to find what is the speed at the third second, how small would we want our h value to be? As small as possible, 0 plus. Almost 0, right? So now we can say that the best answer for the speed at the third second would be when this h turns to almost 0. And so we can say that the speed at the third second is exactly 6 meters per second, since we can ignore the h, arguing that it's very small. A very important point though, here in the second last step, notice that I've easily cancelled out the h. Understand, I could only do that and say that the answer is simply 6 because we are claiming that h is never 0. We do want to observe it for a tiny amount of time, but it is still greater than 0. So here h was finally taken as a number which is greater than 0, not equal to 0. If h were equal to 0, then we could not have cancelled this. 0 by 0 becomes indeterminate. But we don't have that complicacy here because h will never really be 0. And so we could simply cancel them out. And so the answer is simply 6 meters per second. And so now using the same strategy, we may solve this question in general. I mean, instead of finding out what is the speed of the body at the third second or the 5th second or the 10th second, we may now just try to answer what is the speed of the body at the tth second. That is, instead of going from t equal to 3 to 3 plus h, we have to observe the body at some variable t seconds to t plus h seconds, like I've written over here. So where would the body be at x is equals to t? Well, this tells me that it will be at t square. And then where would the body be at t plus h second? It will be at t plus h whole square. Then what would be the distance covered in these h seconds? T plus h whole square minus t square divided by time taken, which is h seconds. And then we would have a very similar calculation. Let me do that in fact. T plus h whole square minus t square divided by h is equal to t square plus 2th plus h square minus t square divided by h. The t squares get cancelled. We are left with 2th plus h square in the numerator. I can factor out an h, so I get 2t plus h. We can cancel out the h because h is not equal to 0. It's always greater than 0 and we get 2t plus h. Can you see it? So basically this is the average speed over these h seconds, and to get the answer for what is the speed at the tth second, we would want the value of h to be as small as possible. So to give the accurate answer, we'll just drop the h, make it almost 0. So what answer do we get? 2t. See, now it makes sense. When we solved this for t equal to 3, we saw that at the third second the body is at 6 meters per second. 2 into 3 is 6. How fast? What would the speedometer show at the 5th second? 10 meters per second. We always knew that the speed of the body is increasing with time because of how the position was changing with time, x equal to t square. But now we have also figured out what is the value of the speed at any time. So now we not only know that the speed is increasing with time, we know what exactly is the speed at different times. At the 11th second, what is the speed? 22 meters per second. Now some of you might have gotten to this result without so much mess by observing that here the position depends on the square of time, and that happens for a body that is uniformly accelerated. And you know that because you've studied the equations of motions in class 9. The second equation of motion said s is equals to ut plus half at squared. See, here the position is depending on the square of time. So if we forcefully write this equation equation in the form s is equals to ut plus half at square. Let me write it. See, I've written it in the form ut plus half at square. Since because I only wanted a t square, I've put 0 into t, that's my ut, plus, so this part is 0. Now this part has to be a t square. Because I have to write a half, I've put in a 2 to cancel them out and finally get a t square. And now we can say that since we were able to write the position of the body in the form ut plus half at square, this must be a body that is having a constant acceleration. And the acceleration value is 2, half a t square, right? We can compare and say that the initial velocity of this body is 0 and the acceleration of the body is 2. Let's note it. So now if this body is a uniformly accelerated body with an initial velocity of 0 and a constant acceleration of 2 meters per second square, its velocity at time t can be given by the first equation of motion. V is equal to u plus at, and here u is 0 and a is 2. So V is equals to 0 plus 2t. So V is equals to 2t. That is the result that we finally got, which means you could have avoided the mess for this particular equation. Because even though this is not as convenient as the last case where the body was moving at a constant speed, this body is still convenient because this body is having a constant acceleration. And we've learned in class 9 how to deal with a body that has a constant acceleration. But that does not mean that our efforts have gone to vain. Because if you have a situation like this one, where the position is depending on the cube of time, now you're no longer dealing with a body that has a uniform acceleration. You can't rewrite this body, you can't rewrite this equation in the form ut plus half at square. It's no longer a quadratic equation. So not only is the position of this body changing with time, not only is the velocity of the body changing with time, but also the acceleration of this body is changing with time. It's actually increasing with time. So here, since the acceleration is not a constant, we can't simply say V is equals to u plus at. A is not a constant. Even the value of A will change with time. So in order to calculate what is the speed of this body at the tth second, we must go through the approach of h. We'll first get an expression for what is the average speed over the h second interval and then enforce the value of h to be 0 plus. Let's do it here. At t, where would the body be? At t cube, because x is equals to t cube. And at t plus h, where would the body be? T plus h whole cube. And then the difference in the position will tell me the distance covered over those h seconds. Let me write it. Now it's all calculations from here. Just watch. You people know how to expand a plus b whole cube, right? A cube plus 3a square b plus 3ab square, 3ab square plus b cube. Again, the plus t cube cancels with the minus t cube. I can factor out an h from the numerator. It's in every term. H can be cancelled out because it is never really 0. It's 0 plus. So this really becomes the expression for average speed over the h second interval. If we want to know what is the speed at the tth second, we want the h value to be 0 plus. If we put almost 0 in place of h, this term, because it has a h, and this term because it has a h, can simply be ignored. And we can say that the answer is 3t square. Now if you've already started to study a little bit of class 11 physics and they've asked you to memorize differentiation formulas, you might have started to notice that they ask you to memorize that the differentiation of t cube with respect to t would be 3t square. And similarly, the differentiation of t square with respect to t is 2t. And this is what I wanted you to understand. See, here we had two dependent quantities, position and time. So if the value of time would change, the value of position would also change. In my first very example, the change in position and change in time always had the fixed ratio for a body moving with constant speed. But in the subsequent examples, we saw that it may not always be the case. The value of change in x by change in time may not always be a constant. And then we became interested in calculating that for a very tiny change in time, what is that tiny change in x? And that calculation has led us to the answer of 3t square in this case. And this is what exactly differentiation is. When there are two dependent quantities and you're trying to measure how much does the second quantity change, when the first quantity is changed ever so slightly, this measurement is nothing but differentiation. If y depends on x, change in y divided by change in x, where the change in x is extremely small, 0 plus, then this change in y by change in x, this ratio is called the differentiation of y with respect to x. In our examples, the differentiation of position with respect to time, that is measuring this ratio, change in position by the time taken, where the time taken is extremely small, allowed us to calculate the velocity at a certain moment. And so we say that the velocity of a body at a certain moment is the differentiation of its position with respect to time. In fact, in class 9 also you were making these calculations, change in position, which is basically displacement divided by time taken. Recall that used to give you the average velocity. It's giving you the average velocity because these changes in times were significant long intervals of time. But if the time interval taken is extremely short, 0 plus, then that average velocity actually converges to the measurement of velocity of a moment. And so we can say this is the formula for the velocity at a moment. But we must write that in this formula, the time taken must be extremely small. Only if we mention this, the formula for velocity at a moment be different from the formula for the average velocity. In fact, here you can see that change in symbol is a triangle, right? And here also we are writing change in position and the change in time. But when this change is extremely small, instead of the triangle, we use a different symbol to indicate it's not just any change, but a very small change. Do you know what that symbol is? It's d, the lowercase d of English. So I could rewrite this as dx by dt. So the person who reads this understands that you're trying to write change in position by change in time. But because you're using a small letter d, it means that the change in time taken has to be extremely small, 0 plus. This is also sometimes read as the differentiation of x with respect to time. So all in all, what really is dy by dx? If y depends on x, if you change x, y will also change. And you're just calculating that ratio, change in x divided by the corresponding change in y. But if the change that you took in x is infinitely small, then that very ratio is nothing but dy by dx. Also read as the differentiation of y with respect to x. So for example, if y was equal to x square, we already worked with this case. Remember, position was equal to t square, and then when we took a small change in t, we got a small change in position. Now instead of position, if we wrote y, and instead of time we wrote x, right? Y is equals to x square. We'll find that that ratio, change in position by change in time, now would be dy by dx, and the answer would be 2x. Remember, we got 2t. Similarly, if you have y is equals to x cube, then dy by dx would be 3x square. In fact, I want to hint you towards something here. If y is equals to x to the power n, then dy by dx will be n times x to the power n minus 1. You see, these two answers follow what I've written here. Here n was 3. So see, we got 3 times x to the power 3 minus 1. Here n was 2, so we got 2 times x to the power 2 minus 1. These results seem to follow this general behavior. So is this statement true? If the dependence between y and x were such that y is equals to x to the power n, can you calculate change in y by change in x, where the change in x is very small, and really prove the fact that dy by dx is this? You have to do it the same way. When the value is x, the value of y is x to the power n. But when the value of x changes from x to x plus h, then the value of y will change from x to the power n to x plus h to the power n. And then we need to calculate the ratio, the change in y by change in x. Very similar to what we were doing. We are changing x by an amount h. Of course, later we want that h to be 0 plus. But the working begins this way. The change in y would be this minus this. Change in x is simply h. And then we need to make calculations. But the bad news is that when we had y equal to x square or y equal to x cube, we knew how to expand x plus h whole square or x plus h whole cube. Now we have x plus h to the power n. How do we hope to expand this? You might not know that yet, but I want you to think all of what we discussed today, and even this, how to expand x plus h to the power n, was thought through by the gentleman Isaac Newton more than 300 years back. And now I want you to think about it. And don't worry if you fail. I'm going to teach you how to expand this.